Thermodynamic study of micellization of SDBS in aqueous and in binary solvent systems of ethylene glycol. Abstract knowledge of micellar behavior of surfactants in aqueous and in co-solvent system is essential for wide range of applications. Association behavior of an anionic surfactant, sodium dodecylbenzenesulphonate, SDBS, has been studied conductometrically at different temperatures in aqueous and in various compositions of ethylene glycol, e.g., and water. The critical micelle concentration, CMC, and degree of counter-ion dissociation values, A, of SDBS increase as the mole fraction of ethylene glycol, e.g., increase at constant temperature and also increase with increasing temperature at constant mixture composition. Phase separation model, which gives quantitative theoretical interpretation of thermodynamic parameters of micellization to evaluate the free energy, enthalpy, and entropy of micellization over the temperature range of 298-318 K. The thermodynamic analysis shows that, although the micellization is less favorable in mixed solvent compared to pure water, but the process is spontaneous and exothermic. It was found that the free energy of micellization values become less negative, whereas the enthalpy values becomes more negative in binary solvent systems than aqueous solution. The .SOM values for aqueous solution of SDBS are higher than that of binary solvent systems. That micellization is favored by entropy gain in aqueous solution. Keywords: micellization, SDBS, ethylene glycol, thermodynamics. Introduction. In recent years there has been a great interest on the study of self-assembly properties of surfactant in solvent medium containing a binary mixture of water and polar/non-polar solvents 1, 2, 3, 4. It is well known that surfactant molecules are associated into micelles above the critical micelle concentration, CMC, and self-association of surfactant is dependent on many factors but largely dependent on nature of the solvent as well as temperature of the solution. Inclusion of different types of solvents influences the micellar properties by affecting the solvent structure or morphology. The addition of co-solvent in aqueous medium is of considerable interest since the applications of surfactants in industrial process like cleaning operation, lubrication, oil wetting cleaners, etc., which require water-free or poor water medium. 5. Aggregation behavior of surfactant in solvents other than water, non-aqueous, is considerably dependent on solvent polarity and its ability to form hydrogen bond in solution. Micellization can be possible in solvents such as ethylene glycol, hydrazine, formamide, glycerol, which have high degree of hydrogen bonding 6, 7, 8, 9. On the other hand, micelle formation is also possible in solvents like acetone, acetonitrile, and dimethyl sulfoxide where the hydrogen bonding ability is less 10, 11. Beside hydrogen bonding ability, hydrophobicity of the solvent also plays a significant role in micellization process. Micellization process of ionic and non-ionic surfactants in presence of co-solvent has been studied by many investigators. A.D. Fenta investigated the surface and thermodynamic studies of surfactant, SDS, HTAB, and tween-80, in binary mixtures of 1,2-ethanediol, e.g., and 1,2,3-propanetriol, PG, with water by applying conductance, surface tension, and dissolubilization, UV-vis absorption spectroscopy, techniques 12. In another thermodynamic study, K. Prajapti and S. Patel have been studied the micellization of SDS, C16TABR, and tween-80 in EG/water and formamide water mixed solvent using surface tension, viscosity and conductance measurements 13. K. Gracie et al. Has been reported the micellar properties of sodium dodecylsulfate, SDS, in aqueous binary mixtures of ethylene glycol, e.g., using various techniques such as conductivity, density, EMF, surface tension, viscosity, ultrasonic velocity, and spectroscopy, fluorescence. They were also calculated the thermodynamics of micellization from the temperature dependence of CMC values 7. Seolazerny et al. Has been investigated the micellization behavior of cetyl trimethylammonium bromide, CTABR, in ethylene glycol, e.g., dimethyl sulfoxide, DMSO, and dimethylformamide, DMF, water mixed solvents, using electrical conductivity measurement at different temperatures. 11. Glycols are well known for their use as coolants and antifreezes and find application in pharmaceutical, cosmetics, and food industries. 14. In most these applications, surfactant is also present, and therefore it is important to study the effect of glycol on micellization of surfactant. Materials and method. Anionic surfactant, SDBS, purchased from Sigma Aldrich and used as received. Ethylene glycol is a polar, colorless, viscous liquid, obtained from Merck Private Limited and used without further purification. Conductivity water was used for preparing all solutions. Conductance measurements. Concentrated stock solutions, 10 to 15 times the CMC, of SDBS were prepared individually in pure aqueous and in different compositions of binary solvent of e.g. with water. The conductivity measurements were performed with digital Sistronics conductivity meter, 306. Initially 25 ml of solvent, water/binary mixture of solvent, was placed in a beaker and concentrated surfactant solution, prepared in the desired solvent medium, of known concentration was progressively added in solvent. The temperature of the solution was maintained by temperature-controlled circulator water bath, holding the solution under study to maintain the desired temperature. The specific conductance of the solution was observed after each addition, followed mixing on magnetic stirrer and attaining temperature equilibrium of system. The procedure was repeated for different temperatures, and CMC of SDBS was obtained from the breakpoint in the conductance versus concentration plot. Results and discussion. Effect of ethylene glycol on CMC and degree of ionization. The specific conductance of SDBS was observed from pre-micellar concentration to post-micellar concentration in aqueous and in binary solvent systems of e.g. 5%, 15%, and 25%, with water at 298 K. The specific conductance plotted against molar concentration of surfactant and the concentration corresponding to the intersection of these two lines gives the CMC, i.e. point of aggregation, of SDBS, Figure 1. The CMC value of SDBS in pure aqueous medium obtained are in good agreement with literature values. 15. The ratio of the slopes of post-micellar region to pre-micellar region gives the degree of ionization, A, of the surfactant. It has been observed that when the solvent system changes from aqueous to binary solvent systems at specific temperature, the CMC and degree of ionization values of SDBS increase, Table 1. The increase of CMC with ethylene glycol concentration can be explained on the basis of change in the bulk phase properties, e.g. dielectric constant, dipole moment, viscosity, etc., of the solvent system. 16. On addition of e.g. fractions in aqueous solution causes decrease of the dielectric constant of binary solvent system because e.g. dielectric constant equals 37.7 is lower than water equals 78.54, so lowering of dielectric constant would result in an increase in the repulsion between the ionic head groups, leading to delayed micellization. Ethylene glycol has a high degree of hydrogen bonding, presence of two O groups, and act as a water structure breaker, ability to form intermolecular H bonds with water. 17. It would facilitate the interaction between the hydrocarbon part of organic solvent and hydrophobic tail of the surfactant molecule. Hence difficult for the hydrocarbon chain of surfactant to aggregate due to solvation of them, and so the lesser number of monomer to form micelles, and hence increase the CMC of surfactant. 18. An increase in degree of ionization with respect to solvent percentage is expected due to decreased charge density on the micellar surface caused by a reduction of the micellar aggregation number. 19. Another fact is viscosity of the medium also increases on increasing the percent of e.g. in water, and it becomes difficult for surfactant tail to migrate easily from bulk phase to the micellar phase, result in the increase of CMC of surfactant. 0.00.5 1.01.5 2.0 2.5 3.0 3.5 4.0 0.0 0.2 0.4 0.6 0.8 1.0 1.2 1.4 1.6 1.8 Aqueous 5% e.g. 15% e.g. 25% e.g. Specific conductance, MSCM1, SDBS Effect of e.g. Effect of temperature on CMC and degree of ionization. The plots of specific conductance and molar concentration of SDBS for aqueous and binary solvent systems at different temperatures are presented in Figure 2. The CMC values of SDBS in water and in binary solvent systems, 5%, 15%, and 25%, of EG and water increase with increase of temperature, Table 1, Figure 3. Increased thermal motion on increasing the temperature is responsible for the disruption of the water structure surrounding the alkyl tail part of ionic surfactants, which opposes the micellization, and inhibits the formation of ordered structure of micelles 11,20. Another fact is the dehydration of surfactant ionic head groups at elevated temperatures, resulting in a stronger repulsion of their ionic heads which disfavor the formation of micelles 21. The degree of ionization value also increase with temperature, Table 1 Figure 4, and it could be attributed to the fact that thermal forces increases the separation between the ionic head groups and counter ions 11. The values of free energy of micellization, degree, are found negative, degree 0, for SDBS in aqueous as well as in binary solvent systems at different temperatures. It could be due to increase of CMC with temperature in both systems, aqueous and binary solvent systems, studied. The fractions of EG increases at specific temperature, the micellization process become less spontaneous, Table 2. The addition of glycol decrease the dielectric constant of medium and that result in the decrease of aggregation number, hence surfactant monomers in bulk phase of solution increases. So that the degree of ionization, A, values and CMC values increase which further decrease the negative value of, degree, EQ1. Another fact for the free energy of micellization becomes less negative in binary solvent systems of EG is that there may be different types of free energy associated with micellization process. It is mainly controlled by surfactant tail transfer, that accounted for the effect of co-solvent on the micellization process 23, which is defined by the expression. It is found that free energy of surfactant tail transfer, are positive and increase with increasing solvent fractions, e.g., in the micellar system at specific temperature, Table 3. It indicates that micellization is less spontaneous in binary solvent systems, thus apparent that transfer of surfactant hydrophobic tail from bulk phase to micelle phase is less spontaneous. The values of enthalpy of micellization, are found to be negative and becomes more negative with increasing temperature as well as with increase in the volume fraction of EG in aqueous medium, Table 2. It is clear that the enthalpy change favors the process of micellization and proceeds via an exothermic process. The negative is associated with the hydrophobic interaction in the interior of the micelle with the release of more arranged water molecules, or melting of the iceberg, surrounded to hydrophobic tail of the monomer. It becomes more exothermic as the temperature increases because at higher temperature the hydrogen bond between the water molecules is diminished. Consequently, less energy is required to break up the iceberg water structure around hydrophobic alkyl chains 24. The enthalpy of micellization is found more negative as the EG content increases due to formation of more intermolecular hydrogen bonds between EG and water. The results of entropy of micellization for SDBS are given in Table 2 and found that, values are positive for each solvent system, indicates that the micellization is favored by entropy gain. The positive value of, indicates that the micellization process is governed with the destruction of the iceberg around the hydrophobic alkyl chain. The decrease of, values with increasing temperature in aqueous as well as in binary solvent systems, suggest that disordering of water molecules becomes less pronounced with increasing temperature because as temperature increases, the structured water layer around the hydrophobic tail of a monomer becomes thinner, degree of structure in the water layer decrease. Therefore the extent of randomness decreases with increasing temperature. 24. Although the magnitude of is lower in the presence of co-solvent compare with aqueous surfactant solution, but positive value of entropy indicates that the solvent, e.g., still control the three-dimensional water structure and increase orderliness of water by intermolecular hydrogen bonding with ethylene glycol. 11. It can be attributed from the results of study that the micellization process is favored by enthalpy gain at higher temperature and entropy driven at lower temperature. Conclusion. Investigation carried out in surfactant binary solvent systems has considerable attention due to their wide range of applications in water-free or poor water medium. Both the addition of co-solvent, ethylene glycol, and rise in temperature results in an increase in the critical micelle concentration, CMC, and degree of ionization for studied surfactant. Due to change in bulk phase properties of binary solvent systems are responsible for unfavorable micellization in binary solvent systems. Thermal agitation causes disruption of water molecules surrounding the alkyl tail part of surfactant and hence the CMC increases for both systems. According to thermodynamics of micellization decrease in free energy of system suggesting micellization is spontaneous and favorable but increase in temperature and addition of e.g. in water decreases the spontaneity of micellization of SDBS surfactant. Micellization is favored by enthalpy change at higher temperature and entropy gain at lower temperature. Knowledge of CMC and thermodynamics of micellization are essential for understanding spontaneity and stability. It would be beneficial for various types of applications like cleaning, lubrications, pharmaceutical, cosmetic, petroleum and mineral processing etc. which require lesser amount of water.